Well, you see, before we step into the strange realm of neutron stars, let me ask you something. Have you ever looked up at the night sky and wondered what becomes of a giant star when its life finally folds in on itself? Imagine a world no wider than a city, yet so heavy it could outweigh our sun. A place where atoms are squeezed until there is no space left between them, where matter becomes something almost mythical. And perhaps, if you close your eyes for a moment, you might sense it, that quiet heartbeat of a collapsed star, still echoing across the dark. I suppose the question is this: what secrets are locked inside these cosmic remnants, these tiny titans born from the death of giants? And why do they pull us in with such irresistible curiosity? Neutron stars are, in a way, the universe holding up a mirror, reminding us how fragile and yet how extraordinary matter can be. They are the afterlives of stars, the compressed memories of celestial fire. And as we drift deeper into 2025, we find ourselves listening more closely to them, as though they're whispering truths about the fabric of reality itself. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we first try to describe what a neutron star truly is, we find ourselves standing at the threshold of something both simple and impossibly strange. A neutron star is, in the quietest sense, the remnant of a massive star that has exhausted everything it had to burn. And yet, that simplicity hides a depth that can swallow your breath. Imagine, the way a memory lingers after a life has passed. A neutron star is a kind of cosmic memory, the dense leftover core of a supergiant that once burned with a brilliance so intense it could sculpt space around it. When that star collapses, all its fire extinguished, what remains is this compact sphere, perhaps no wider than a city, but holding within it a gravity so fierce it bends not only the space around it, but our understanding of matter itself. And that's the thing. A neutron star is not alive, not in any familiar sense. It does not shine by fusing hydrogen the way our sun does. Instead, its light is a kind of echo, a leftover glow from the violence that birthed it, and from the strange internal motions taking place beneath its crust. You might picture it as a coal left from a vast celestial bonfire, though far hotter and far more exotic than any ember we know. At its surface, the star radiates primarily high-energy light, from X-rays to gamma rays, flickering like some distant reminder of the furnace it once was. It is a dead star, yes, but death in the universe rarely means silence. It often means transformation. And perhaps the most remarkable transformation is what happens to the atoms inside it. You know, an ordinary atom is mostly empty space. The nucleus sits like a tiny weight at its heart, and electrons flit around it like dancers on a stage far larger than themselves. But inside a neutron star, that vast emptiness is squeezed away. Atoms are pushed into one another until their structures fail, their identities blur, and protons and electrons merge into neutrons. Matter becomes a single ocean of particles packed so tightly that a teaspoon of it would outweigh mountains. It is the universe displaying its talent for extremes, showing us a version of matter we cannot hold, cannot recreate, and can barely imagine. And, this star, this collapsed relic, is astonishingly dense even by cosmic standards. Its diameter may be only around 20 kilometers, smaller than a morning commute, and yet it carries more mass than the sun that warms our planet. Imagine cradling an object the size of your neighborhood in your palms, only to find it has the weight of entire worlds. The mind cannot truly hold this idea without stretching. But that stretching is good. It reminds us that the universe is not obligated to remain within the boundaries of our intuition. Sometimes it surprises us. Sometimes it humbles us. What is also beautiful, in a quiet and perhaps unsettling way, is that a neutron star no longer burns. There is no nuclear fire within it, no bright furnace churning hydrogen into helium. Instead, it is a place shaped entirely by gravity, by pressure, by the collapse of particles into a new order. It is in many ways the closest thing we have to a natural laboratory for the physics of extremes, where the familiar rules strain and sometimes break. And I suppose that is why scientists look to neutron stars with a kind of reverence. They are not simply objects, they are questions made manifest. Because, well, think about it. If a neutron star is the grave of a massive star, then its existence forces us to confront the strange truth that destruction and creation are forever entangled in the cosmos. A star dies, and yet from that death emerges something new, something fiercer, denser, stranger than what came before. It is as if the universe were saying that endings are merely new states of being, new shapes for the same ancient matter. And when you peer at one of these stars, through a telescope or through the shared imagination of science, you are looking not only at the residue of a supernova, but at a boundary. A neutron star sits at the edge of what matter can become before it collapses even further into a black hole. It is the threshold before light loses the ability to escape. And perhaps that makes neutron stars feel like guardians of some deeper truth, standing between the familiar and the unknowable. What fascinates me is that although they are so dense, so dark compared to ordinary stars, neutron stars are not silent in the cosmic conversation. Their magnetic fields channel radiation, their rotations generate pulses, and their intense gravity sculpts the orbits of nearby stars. They speak through signals that cross millions of years before reaching us. And perhaps you and I, as we sit here in the gentle quiet of this moment, are hearing echoes that began before human beings had even formed the words to wonder at them. You know, when I picture a neutron star suspended in the vastness of space, I imagine its surface as a kind of crust of crystalline neutron matter, unbelievably solid, unbelievably thin. Beneath it lies a world so alien that our physics struggles to describe it. But at this early stage of our journey, we can simply hold on to the idea that a neutron star is not merely an object, it is a story of collapse, of transformation, of the strange beauty hidden in the ashes of things that once burned brightly. And as we drift through 2025, continuing our gentle exploration of the universe, we keep returning to these objects because they remind us of something essential. They remind us that even the most familiar materials can take on unimaginable forms under the right conditions, and that the universe is forever reshaping itself, folding and unfolding matter like a cosmic origami artist. Perhaps that is why neutron stars feel so compelling, even comforting in a strange way. They show us that there is structure in ruin, that even in the violent death of a star, the universe does not waste anything. It rearranges, it compresses, it transforms. And from that transformation emerges a beacon, a compact star radiating its residual energy into the infinite dark, whispering a reminder that even the remnants of destruction can illuminate the cosmos. And I suppose now, as we've lingered with this first understanding of what a neutron star is, we naturally begin to wonder how such an impossible object is born. What kind of cosmic pressures must gather, what kind of collapse must unfold, to create a star where atoms themselves dissolve into pure density? That question, you see, leads us gently toward the next chapter in our journey, where the death of a massive star becomes the birthplace of something far stranger. Well, you see, once we begin to wonder how such an impossible object as a neutron star actually comes into being, we find ourselves drifting backward through its history, peeling away layers of collapse and fire until we stand beside the dying breath of a massive star. And, perhaps this is where the story truly begins, with a star far larger than our sun, a giant that has spent millions of years holding itself up against the crushing force of its own gravity. Inside it, in those deep, burning chambers, nuclear fusion has been at work, turning simple elements into heavier ones and releasing vast amounts of energy that keep the star swollen and shining. But no star burns forever. Even the greatest of them carry a quiet countdown within. And that's the thing. When the star exhausts its fuel, when the last of the nuclear reactions sputter and fade, gravity that has been held at bay for so long finally pushes inward. Imagine a moment of cosmic betrayal, the star losing the inner fire that kept its structure intact, and suddenly its core begins to fall. You know, the speed of this collapse is astonishing. The core doesn't drift inward gently, it plunges. It compresses faster than thought, faster than intuition, until protons and electrons are forced so tightly together that they fuse into neutrons. In that instant, everything the star once was becomes unrecognizable. The atoms that made up its core are shattered, their structures erased. What remains is something like a fluid of nucleons, a pressure born from the fundamental forces that ordinarily stay quiet inside atomic hearts. Perhaps you can picture it like this. The star's collapse is so intense that the inner worlds of matter are peeled open. The familiar architecture of protons and electrons no longer survives. Their merging releases a pulse of neutrinos, ghostly particles that race outward, carrying away energy and marking the moment when the core stops collapsing just long enough to stiffen into what will become a neutron star. And then, well, something extraordinary happens. The outer layers of the star, still racing inward, slam into this suddenly rigid core. It is like watching an avalanche strike an immovable wall. The impact creates a shock wave so powerful it rips through the star's remaining layers and blasts them into space. This is the supernova, one of the most energetic events the universe knows how to produce. For a brief time, the explosion can outshine entire galaxies, and, if you were standing light years away, you might see that sudden bloom of brilliance and feel, without fully knowing why, that something ancient had ended and something unimaginable had just been born. But not every collapse creates a neutron star. The universe, has a way of choosing outcomes with quiet precision. If the collapsing core is too massive, its own weight overpowers even the neutron pressure-resisting collapse, and the core falls beyond recovery, becoming a black hole. A neutron star exists only in that delicate in-between space, where gravity is immense but not infinite, where matter can still hold itself together at densities beyond our comprehension. And I suppose this makes each neutron star a kind of survivor, balanced on the edge between two cosmic destinies. When the core mass is just right, the neutron star remains. The rest of the star, its outer shells, are flung into the dark, enriching the surrounding space with heavy elements forged during the explosion, calcium for bones, iron for blood, gold for rings, all scattered into future worlds. It is strange to think that the detritus of a dying star becomes the raw material for life, worlds, civilizations. But in the quiet hours of 2025, if you were to look at your own hands, you might see the faint memory of stars long dead shimmering beneath the skin. Now, back to the core itself. As it settles into its compact state, something remarkable is happening inside. The neutrons crowd so densely that the material cannot compress further without breaking physics as we know it. This neutron degeneracy pressure pushes back against gravity's inward pull. It is a standoff between two titanic forces, collapse and resistance. And in that delicate, trembling balance, a neutron star stabilizes. It becomes a cosmic relic that refuses to shrink any further unless additional mass pushes it past its limits. But the formation story does not end with the creation of the neutron star. There is a kind of cosmic aftermath to consider. The explosion sends shockwaves into interstellar space, carving out cavities, igniting nearby gas clouds, even triggering new waves of star formation. It is as though the death of one massive star becomes the spark for entire generations of new ones. And floating in the center of that expanding debris field is the newborn neutron star, still glowing with residual heat, still spinning rapidly because the collapse has forced its rotation to speed up. Like a figure skater pulling their arms inward, The star's spin intensifies as its radius shrinks. What once may have been a leisurely rotation now becomes hundreds of revolutions per second. Perhaps you can imagine standing above the poles of this new star, watching it settle into existence amid the debris of what it once was. The surrounding material continues to drift outward, forming an expanding shell of hot gas and dust. This is the supernova remnant, a cosmic bruise glowing long after the star itself has transformed, and buried within it, almost shyly, sits the neutron star, a pinprick of impossible density in a sea of glowing ruins. One of the subtler truths is that core collapse is not always symmetrical. If the explosion is lopsided, the neutron star can be kicked across space at astonishing speeds, like a stone struck by a slingshot. Some of them travel hundreds of kilometers per second, wandering the galaxy as solitary travelers, carrying the story of their violent birth with them. Others remain embedded in their remnants, quietly cooling, slowly spinning down, but still radiating an imprint of the forces that forged them. You see, the process that forces protons and electrons into neutrons is not simply compression, it is physics under duress, matter pushed beyond its comfort, beyond the shapes we normally expect it to hold. A neutron star is, in that sense, not only a monument to stellar death, but a testament to the universe's capacity for reinvention. The collapse erases the old identity of the star and ushers in a new one far more extreme, far more compact, and far more mysterious. And I suppose what makes this transformation particularly beautiful is the idea that the star's outer layers, once held together by the same light that sustained it, are now freed to participate in a much broader cosmic cycle. These shells of matter become part of nebulae, part of future solar systems, part of worlds not yet imagined. Meanwhile, deep inside the heart of the explosion, the neutron star remains as a kind of cosmic punctuation mark, the final statement of the star that once was. As we move through this story, something else becomes clear. The birth of a neutron star is not merely the collapse of a structure, but the revelation of a hidden layer of physical laws. During core collapse, densities rise so high that the ordinary rules governing atoms break apart. Quantum mechanical forces, normally buried inside nuclei, become the architects of macroscopic objects. In a neutron star, the smallest scales of nature shape something we can see from across galaxies. Perhaps this is why scientists describe these stars as natural laboratories for extreme physics. They are places where matter behaves in ways we cannot duplicate in our laboratories on Earth. You know, if we were to follow the journey of one collapsing star in slow motion, we would see its final moments unfold in a heartbeat. First, the core contracts, then neutrinos burst outward, then the shockwave races through the star's body and detonates the supernova. What is left afterwards seems almost calm by comparison, a small, dense, cooling object quietly spinning in the dark. The surrounding debris slowly expands until it becomes part of the interstellar medium. And somewhere within that quiet relic lies the memory of forces so intense they reshape the very nature of matter. And yet, perhaps the deepest wonder of all is that the universe produces these stars routinely. Throughout the galaxy, massive stars are living, burning, collapsing, exploding, and leaving behind these neutron-rich cores. The process is violent, yes, but also astonishingly efficient. Not all stars will undergo this transformation. Only those with sufficient mass are destined for such a dramatic end. Too small, and the star becomes a white dwarf. Too large, and the collapse overshoots into a black hole. In between lies this narrow corridor where neutron stars are born, a corridor defined by mass, pressure, and the ability of neutrons to resist further collapse. When you step back for a moment and look at this entire arc of transformation, you might feel a strange sense of cosmic symmetry. The universe, after all, recycles everything. What collapses becomes fuel for something else. What is destroyed becomes structure for future worlds. And the neutron star, sitting silently within the expanding shell of the explosion, becomes a reminder that even in ruin, there can be remarkable order. And now that we have walked through the fire and collapse, through the intense pressures that reshape matter and the explosive force that tears a star apart, we find ourselves standing beside this newborn neutron star, bathed in the faint glow of its still cooling surface. Perhaps you can feel the weight of it, the density, the impossible concentration of matter. And naturally, the next question that arises is simple enough. What does matter become under such pressure, such compression, such overwhelming force? What is the nature of density when it reaches the limits of what physics can describe? And that gentle curiosity leads us onward, toward the next layer of the story, where we explore the staggering density of neutron star matter and the strange physical realities that emerge within such a compact world. Well, you see, once we arrive at the very surface of a newborn neutron star, standing there in imagination as the supernova's glow fades around us, we begin to sense that the true strangeness has only just begun. Everything that happened in the collapse was violent, monumental, transformative. Yes, but what remains after that collapse is a world so dense, so compressed, so profoundly unlike anything we know that even our language struggles to keep up. And, perhaps that is the beauty of this next step. To understand a neutron star is to look directly into the places where matter forgets the shapes it once held, where atoms surrender their identity to pressures that defy every instinct we have about the solidity of things. You know, when we speak of density on Earth, we imagine heavy metals or compact objects we can hold. A kilogram of iron feels substantial in the hand, reassuringly firm. But on a neutron star, the scale changes so dramatically that ordinary comparisons collapse under their own inadequacy. A single teaspoon of neutron star material, if somehow removed from the immense gravity that confines it, would weigh billions of tons. Not millions, but billions. It is almost whimsical how effortlessly the universe stretches the limits of our intuition, inviting us to picture holding in our palm a droplet that outweighs mountains. This density arises because atoms, those delicate architectures of mostly empty space, have been stripped of their structure. In the crushing collapse of the star's core, electrons were forced into protons, producing a vast sea of neutrons packed together in a way that atoms in the ordinary universe never experience. The emptiness inside them is erased. There is no space left for the orbit of electrons, no shimmering cloud of probability. Only neutrons pressed shoulder to shoulder, forming a kind of nuclear fluid, a soup of tightly bound particles that behave collectively rather than individually. And that's the thing. This is matter pushed beyond the threshold of familiarity, beyond the domains where everyday physics feels comfortable. Perhaps you can imagine dipping your hand into such a material, though of course the reality would shred you faster than thought. Still, as a thought experiment, picture a substance so dense that your fingers cannot move through it, not because it is solid, but because it is so tightly compressed, it resists deformation with unimaginable force. It is something like the density of an atomic nucleus, yet extended across an entire star. The universe took the heart of an atom, scaled it up, and made a world out of it. And, the pressures inside this star are far beyond anything we can create on Earth. Even our most advanced laboratories, our particle accelerators, our high-energy experiments, cannot recreate the sustained densities found in a neutron star's core. They are places where quantum mechanical principles rise from the microscopic to the cosmic, shaping landscapes made of neutrons instead of mountains. In this sense, a neutron star becomes a kind of cosmic laboratory, one that we can observe but never touch, a place where matter reveals what it becomes under conditions that seldom occur anywhere else. If we stood on the surface, time itself would behave differently. Gravity is so strong that it distorts the flow of time, slowing it compared with the rhythm we know. A second on the surface of a neutron star would stretch compared to a second measured far away. And perhaps, in a quiet way, that is one of the most poetic truths about these objects. They are places where time bends under the weight of existence, where the river of moments runs sluggishly because gravity holds it back. And you know, even light struggles here. A photon leaving the surface must fight against the gravitational pull of the star, losing energy as it escapes. Its path bends, curving around the star in ways our eyes could scarcely follow. If we tried to look at the horizon of such a world, we might see more than half the sky visible at once, bent upward by the star's intense gravity. The landscape would appear distorted, the curvature of space-time laid bare. And that's the thing about a neutron star. It doesn't merely warp your expectations. It warps the universe around it. One might imagine the surface beneath our feet, though feet are metaphorical here, as a kind of crystalline crust formed from tightly bound neutrons. It is extraordinarily rigid, with a strength exceeding any material we have ever studied. Yet beneath this crust, the density increases further until the matter transitions into a superfluid. Yes, a fluid that flows without friction, without viscosity, moving silently and effortlessly, even as it carries densities beyond comprehension. In this subterranean ocean of neutrons, the laws of fluid dynamics take on exotic forms. Vortices swirl in quantized spirals, behaving like microscopic tornadoes braided through the immense interior. Perhaps the most haunting part of imagining such a world is realizing how smoothly and quietly these extreme conditions exist. There is no roaring fire, no raging plasma storm. The violence happened long before. What remains is a quiet, dense, seamless entity that seems, from afar, deceptively calm. And yet, inside, matter is experiencing pressures so intense that our physics shivers at the thought. The neutron star sits there like a fragment of another universe, a condensed reminder of nature's capacity for extremes. The bending of space-time around it is so steep that even something as intangible as time begins to struggle. If you dropped a clock onto its surface, it would tick more slowly compared to one kept far away. This difference is not poetic exaggeration, but physical truth, a direct consequence of relativity acting on a world of extraordinary mass packed into such a tiny region. And I suppose that is where the philosophical wonder emerges. Neutron stars remind us that time is not absolute. It is a malleable dimension sculpted by gravity. Time is not a clock, it is a landscape we travel through, shaped by the structures of matter that surround us. This extreme density also means that something curious happens to the concept of surface. On Earth, surfaces are comfortable boundaries, but on a neutron star, the crust is barely a facade. The difference between surface and interior is a matter of centimeters before one descends into realms where neutrons swim freely. Standing there would be like balancing on the thinnest shell of stability our universe can muster. Beneath it lies a depth of pressure that could crush any object we know into oblivion. And, perhaps this is why scientists speak with such fascination about neutron star matter. It is symbolic of limits, of the borders where familiar laws begin to fracture. Light struggling to escape, time bending under gravitational pressure, matter collapsing into new forms. It is a natural reminder that the universe contains intricacies beyond our human senses. If you could look at the star from a safe distance, you would see it glowing with thermal radiation, its surface still incredibly hot, though cooling over thousands of years. This radiation climbs out of the gravity well, redshifted, softened, transformed by the effort of escaping. Even photons carry the signature of the star's density, and I suppose that brings us to perhaps the most surprising truth. Neutron stars are the densest stable matter in the observable universe. Only black holes exceed them, and black holes, in their own enigmatic way, are not matter as we ordinarily define it. They are collapses of space-time itself. Neutron stars sit just above that precipice at the limits of what fermionic matter can endure. They are cosmic thresholds, balancing on the fine line between existence and collapse. In the density of this world, in its ability to crush atoms and warp time, we also find clues to one of the universe's more subtle characteristics, the interconnection of forces. Strong nuclear forces, normally confined to atomic nuclei, become the dominant architects of an entire star. Gravity, usually gentle on the scale of our daily lives, becomes so overpowering that it trumps everything else. Quantum effects, typically hidden, define the structure of matter on a scale of kilometers. The star becomes a symphony of forces that rarely play together so loudly. And when you think of it this way, a neutron star is not simply dense, it is profoundly integrated. Every force that shapes the physical universe is at work here, each contributing to the equilibrium. It is a kind of cosmic negotiation, a shared decision between gravity and quantum mechanics about what matter must become under such pressure. Perhaps you can imagine the strange experience of watching an object fall toward this star. As it approaches the surface, tidal forces stretch it into thin strands, pulling at its atomic structure until it becomes a faint smear of disassembled matter. The bending of space-time exaggerates its trajectory, twisting its path, distorting its descent. It is an oddly poetic image, matter returning to its simplest form, surrendering its shape to the immense density of the neutron star. And this is the point, you see, where the physical becomes philosophical. Neutron stars remind us that matter is not fixed in identity. Under enough pressure, enough gravity, enough collapse, everything we think of as solid, stable, familiar can dissolve into something new. They are cosmic metaphors for transformation, endings that become beginnings in strange and unexpected forms. As we move deeper into our understanding of them, feeling the profound density beneath every thought, we naturally begin to wonder what other forces must accompany such crushing compactness. Density alone does not tell the full story. If matter is compressed so intensely, what happens to gravity around it? How does the star's mass influence the space it inhabits, the objects that pass nearby, or the very concept of proximity itself? And so, as we step gently away from the density of this star and let our curiosity drift outward into the space surrounding it, the next question forms almost naturally. What does gravity become when anchored to something as dense as a neutron star? Well, you see, once we begin to talk about gravity on a neutron star, we are no longer speaking about the gentle, familiar pull that keeps our feet on the ground. We are stepping into a realm where gravity becomes something almost mythic in its power, something that stretches the imagination as easily as it stretches matter itself. And perhaps this is the moment when the story deepens, when the star that has already defied all ordinary understanding reveals yet another layer of strangeness. Because the density we have just explored does not sit quietly. It bends space-time so severely that gravity becomes a force beyond comparison. You know, on Earth, we think of gravity as strong enough to pull an apple from a branch or hold oceans against the planet's surface. On a neutron star, gravity is not merely stronger, it is monstrous. It is said to be up to 2 billion times the gravity of Earth. Imagine trying to stand there. Even imagining it feels like a contradiction because no human frame could survive. The moment you approach the surface, you are already being stretched, atoms pulled from atoms, your structure unraveling into a thin stream of particles. There is no standing on a neutron star, no walking, no surviving. The gravity is so intense that it forces matter to obey a harsh new discipline, one where individuality is lost and the star becomes the final sculptor of anything that strays too near. But that's the thing. This gravity does not only affect matter, it also dictates motion in a way that feels almost hypnotic. If you were to drop an object above a neutron star, even from a modest height, it would accelerate to unimaginable speeds in a fraction of a second. Not because of wind, not because of falling through air, but because space-time itself is funneling it downward with relentless urgency. Objects would approach a significant fraction of the speed of light before hitting the surface, releasing energy with such violence that any ordinary material would be vaporized instantly. And, if you imagine watching such a fall, you would see the object distort, stretch, elongate, the star's gravity tugging harder on the near side than the far side. This tidal difference would tear it apart long before it ever reached the ground. Perhaps the most unsettling truth is that nothing can really remain itself in the presence of such gravity. A rock, a spacecraft, a human body, a cloud of dust, even the shape of space-time, all of it is sculpted, deformed, pulled into new forms. It is as though the star is constantly reminding the universe that gravity, when given enough mass in a small enough space, is capable of rewriting reality. And as we drift further in thought, we start to recognize that escaping such gravity is almost impossible. On Earth, escape velocity is a speed an ambitious spacecraft can reach with fuel and engineering. On a neutron star, however, the escape velocity is nearly the speed of light. To flee the star's surface, you would need to move faster than nature allows, so nothing moves away easily. Light itself struggles. Photons climbing out of the gravity well lose energy, their colors stretching into redder wavelengths as they escape. Everything bears the mark of that gravity, like fingerprints pressed into the very nature of motion. Perhaps you might imagine the space around a neutron star as a distorted bowl, the gravitational well so steep that even the pathways of light are curved. If you were safely orbiting at a distance, you could see around the star in uncanny ways because light skims its curved exterior, allowing multiple views of objects behind it. The star behaves almost like a lens, bending illumination from the cosmos around it, shaping perception itself. And this is where the ideas begin to weave into one another. Gravity of this magnitude does not merely affect isolated objects, it affects entire systems. Stars in binary orbits with neutron stars often find their paths twisted into elongated ellipses or tight spirals, the neutron star pulling on them with a ferocity that defies expectation. And if such a pair spirals closer together over time, their dance can end in a collision that sends ripples through space-time itself. These ripples are what we call gravitational waves, gentle quakes in the fabric of the universe, carrying information across unimaginable distances. They whisper the story of two dense stars locked in a cosmic embrace, merging in a moment of unimaginable violence. And perhaps that is one of the most astonishing roles of neutron star gravity. It becomes a tool for testing our deepest theories. The orbits of neutron stars, the bending of light around them, the timing of pulses they emit. These phenomena invite us to test relativity not with blackboards and equations alone, but with real cosmic laboratories scattered throughout the galaxy. Einstein's ideas about space-time curvature and gravitational time dilation are written plainly in the behavior of these stars. A neutron star becomes a classroom for the universe, teaching us what gravity can truly do when given the chance. If one could drift safely, impossibly safely, near such a star, the sensations of space and time would begin to warp. Time would pass more slowly for you compared with someone far away. Clocks would disagree. Distances would feel unnatural. The star does not ask for permission to bend reality. It simply does so by existing. And, that is something quietly humbling. We like to think of the universe as stable, predictable, orderly. But the neutron star reminds us how thin that illusion can be. Mass concentrated into extreme density reshapes the universe around it. It is not only space and time that suffer these distortions, even neighboring stars are affected. The gravity of a neutron star can strip away matter from a companion star, pulling it into swirling disks of luminous material that emit X-rays and other high-energy radiation. Entire atmospheres can be peeled from nearby stars. In this way, a neutron star becomes not only a remnant of a catastrophe, but the cause of new cosmic events. Its gravity feeds it, energizes it, and shapes the environment around it for light years. And yet, in all this intensity, there is remarkable precision. Gravity on a neutron star does not fluctuate wildly. It is consistent, predictable, exacting. It behaves precisely according to the mathematics of general relativity, following space-time curvature like the notes of a cosmic symphony. Perhaps that is part of the wonder. Such overwhelming power coexists with such elegant order. It is brutal, but it is also beautiful in the way it obeys deep principles. As we continue thinking about this immense gravity, we also begin to sense the fragility of the boundary between neutron stars and black holes. If a neutron star were just a little more massive, its gravity would overcome even the neutron degeneracy pressure that holds the star up. It would collapse further, compressing past the limits of matter, falling inward until space-time caves in and a black hole forms. The boundary is thin, The neutron star is perched at the edge of an abyss, maintained only by quantum forces resisting gravitational collapse. This equilibrium creates one of the most intense gravitational environments possible while still allowing the star to have a surface. And, this tenuous balance shapes everything around it. It is what allows neutron stars to exist as independent characters in the cosmic story instead of vanishing behind event horizons. It lets them radiate, pulse, orbit, and interact. It lets them affect nearby stars, produce gravitational waves, and emit streams of particles. It is precisely because they sit at this threshold that they are so scientifically valuable. Now imagine the fate of something unfortunate enough to come too close. The gravity gradients near the surface are so steep that even small differences in proximity can spell doom. A spacecraft approaching the star would be stretched lengthwise, torn into atomic strands before impact. Tidal forces would exceed any structural strength we know. The approach itself becomes a metaphor for encountering cosmic truth, overwhelming, unrelenting, and impossible to endure. And perhaps this is what makes neutron stars so endlessly fascinating. Their gravity is not merely quantitative, it is qualitative. It changes the rules. It reveals what the universe is capable of when mass is pushed to extremes. It shows that gravity, gentle and almost unnoticed in our daily lives, has a deeper nature we rarely glimpse. As we sit here in the soft quiet of 2025, thinking about these distant objects, we might feel a small shiver at the idea that gravity can become so fierce that it can bend the path of light, slow the passage of time, and pull matter apart like threads. Yet in that shiver is also admiration. The universe, in all its vastness, uses neutron stars to demonstrate its more dramatic possibilities. And slowly, as we reflect on all this, another thought begins to stir. If gravity can be so extreme, if it can twist space-time and tear matter into ribbons, what happens when you combine that gravity with motion? What happens when this tiny titan, this condensed remnant of a once burning star, begins to spin? For many neutron stars do not merely sit in stillness. They whirl, turning hundreds of times each second, their surfaces moving at tremendous fractions of the speed of light. And so, as gravity settles in our thoughts like a deep cosmic weight, we are naturally drawn to the next chapter in this journey, where motion joins gravity in a dance so fast, so sharp, so astonishing, that the neutron star becomes not just dense and heavy, but one of the fastest rotating objects the universe has ever crafted. Well, you see, once we've felt the crushing gravity of a neutron star settling into our imagination, the next revelation arrives almost quietly, almost shyly, but with a force that rearranges our sense of motion itself. Because these stars, these tiny, dense remnants of collapsed giants, do not merely sit in the dark as still monuments to their former lives. Many of them spin, and, they do not spin gently the way Earth turns with its slow, deliberate rhythm. They whirl with a ferocity that feels more like an exhale from the universe's earliest moments. They rotate with such incredible speed that even trying to picture it feels like drawing a line with one's mind across the limits of comprehension. Perhaps we should begin by holding something simple in thought: the conservation of angular momentum. It is an idea you already know in your bones. A figure skater pulls their arms inward and spins faster. A diver tucks tightly to twist through the air. And here, in cosmic scale, the same principle unfolds, but with consequences far more dramatic. When a massive star collapses into a tiny sphere, reducing its radius from millions of kilometers to just about 20, the rotational speed must increase. It is not a choice. It is written into the physics of our universe. The star's spin tightens, sharpens, accelerates. What once may have turned leisurely now spins hundreds of times each second. Imagine that. Hundreds of rotations per second. Entire revolutions faster than the blink of an eye. The surface moving with velocities approaching the cosmic speed limit. And the thing is, the star does not seem bothered by this. It simply continues, turning with a determination that feels almost serene in its violence. If you could hover safely above such a star, though of course you cannot, the view would be hypnotic. The crust, smooth and unforgiving, would blur beyond perception, a full rotation happening faster than a heartbeat. The speed would be so great that the star's shape itself distorts slightly, becoming oblate, flattened a bit at the poles by centrifugal force. It resists this distortion, yes, but even neutron star matter cannot remain perfectly spherical when spinning this fast. And if we follow the physics deeper, something even stranger emerges. Beneath the rigid crust lies a superfluid interior, a quantum liquid that can rotate in ways no ordinary fluid can. It forms vortices, quantized threads of rotation arranged with mathematical precision. And as the crust slows over time, ever so slightly due to electromagnetic drag and particle winds, the superfluid interior sometimes resists, creating tensions within the star. These tensions can suddenly snap, causing the entire star to jolt forward in rotation. Astronomers call these events glitches, but that word feels too small. These are the star's internal motions expressing themselves, revealing the mismatched rhythm between crust and core. Perhaps this is one of the quiet wonders of neutron stars. Even their imperfections are cosmic. Even their stumbles teach us physics we could not learn any other way. Now consider how rapidly some neutron stars rotate at birth. When the collapse occurs, the core shrinks so dramatically that rotation rates can spike to unimaginable speeds. We have observed neutron stars spinning more than 700 times per second. 700 full rotations in one heartbeat. Entire mountains of neutron matter swinging around with velocities comparable to beams in particle accelerators. It is almost absurd, almost humorous, that such stability exists in such chaos, and yet the star slows down, slowly, gracefully. Over thousands, millions of years, the rotation decays. The star emits winds of charged particles. Its magnetic field interacts with surrounding space. Energy leaks outward. The spin diminishes. It is as though the star is breathing out its rotation, allowing itself to age. But the slowing is not gentle in every case. Sometimes the interaction with a companion star, if the neutron star happens to have one, can increase its rotation again. Material from the companion spills onto the neutron star, dragging against the magnetic field and accelerating the star's spin. This process can create what astronomers call millisecond pulsars. Neutron stars that rotate hundreds or even thousands of times per second with an astonishing steadiness. They are some of the most stable rotators in the universe, more precise than atomic clocks. The surface speed of such stars is another thing entirely. If a neutron star spins about 700 times per second, the equatorial surface may move at a significant fraction of the speed of light. Imagine that. A world whose crust races so quickly that if a beam of light were to skim along its surface, the star's spin would chase it, not catching it, of course, but keeping a pace that defies instinct. And I suppose what fascinates me most is the balance. The star spins so quickly that it strains against its own cohesion. If it were just a little less dense, just a little less bound by gravity and neutron pressure, it would fly apart like a shattered wheel. But because it is composed of matter so tightly knit, so dense, so fundamentally resistant to deformation, it holds together. The star becomes a demonstration of tension between centripetal and gravitational forces, each demanding something of the other. In all of this rotation, in all of this speed, a neutron star emits a kind of beacon. The magnetic poles do not align with its rotation axis, so as the star spins, beams of radiation sweep across space. These beams, when they cross Earth's path, arrive as pulses, rhythmic, precise, steady, pulses like the ticking of a cosmic lighthouse. And while that belongs more formally to the next chapter, it is impossible not to feel its presence here in the whirring heart of rotation. The spin is the engine. The pulses are the song. And the star's rotation is so deeply tied to its internal structure that studying these rotations allows astronomers to understand what lies beneath the crust. Tiny variations in timing reveal the presence of superfluids, vortex pinning, crust elasticity, and so many other properties we could not otherwise measure. The star becomes not only a spinning relic, but a diagnostic machine, telling us what physics at extreme densities truly looks like. If one could listen, not hear with ears, but with instruments that translate electromagnetic signals into forms we can experience, the rotation would feel like a steady hum, a tone of remarkable consistency. Some neutron stars maintain their rotation with such reliability that their timing could navigate spacecraft with more accuracy than any human-made clock. And that, I suppose, reveals something subtly poetic. A dead star spinning in the dark becomes a guidepost across interstellar distances. Something that has already lived its brightest life becomes a beacon for those just beginning their journey. But even this rotation has its limits. Over long timescales, frictional forces, magnetic braking, and energy loss cause the spin to fade. The star's heartbeat slows, its pulses lengthen, its edges soften. The star ages not by dimming alone, but by relaxing its rotation. And yet, even in old age, the rotation is astonishing. Even a few spins per second for something this dense is a marvel. And perhaps this is the deeper lesson here. The neutron star's rotation is a memory of its past and a promise of its future. A memory of collapse, of conserved momentum, of the violence that shaped it, and a promise that its rotation will continue to influence the universe long after its heat has dimmed. Even in stillness, if such a thing were possible, the story of rotation would live on. As we sit with these thoughts in the quiet of 2025, letting the star's rapid whirling settle into our awareness, another question gently rises. If a neutron star spins at such incredible speeds and emits beams of radiation as it turns, what does that experience look like from afar? What patterns of light and timing does such a star produce? How does a rotating neutron star become one of the most iconic and mesmerizing objects in astronomy? And so, with the star still spinning in our mind's eye, we drift naturally toward the next chapter. The pulsar, the cosmic lighthouse, whose steady beams sweep across the universe like the ticking of an ancient, perfectly tuned clock. Well, you see, once the neutron star begins to spin and its magnetic axis tilts just slightly away from that spin, something breathtaking happens. It begins to sweep the cosmos with light. Not the gentle light of stars we know, but tight, concentrated beams of radiation that flash toward us with a rhythm so steady, so precise, it feels as though the universe itself has learned to keep time. And that is where the pulsar is born. Not as a different kind of star, really, but as a neutron star performing one of the most hypnotic acts in the cosmic theater. When that beam crosses Earth's line of sight, we see a pulse. When it sweeps past again, another, and another. A lighthouse in the darkness of interstellar space. Perhaps the most delightful thing about this is how accidental it is. The star is not trying to signal us. It is merely rotating, and the magnetic field is simply misaligned, and from that misalignment emerges one of the most iconic signatures in astronomy. The pulses can be so regular that they rival the accuracy of atomic clocks. In the quiet of midnight, if you could somehow listen to these pulses translated into sound, you would hear a cosmic metronome, a steady tick-tick-tick echoing across thousands of light years. Imagine for a moment a pulsar spinning hundreds of times per second. Each rotation sweeps the beam like a cosmic lighthouse, but far faster than anything we could build. There are pulsars whose spins reach 700 rotations per second. And, that is not a metaphor. 700 full sweeps in the time it takes to inhale. The star rotates so quickly that the surface could fling you around at a substantial fraction of light speed. Were you somehow able to stand there? The pulses that race past us from such stars become a kind of cosmic heartbeat. You know, these pulses are so consistent that we've used them to measure distances across the galaxy, to test theories of gravity, even to navigate spacecraft. That is one of those wonderful quirks of the universe. Something born from violence, from collapse, from the death of a giant star, becomes a tool for exploration, a beacon that helps us find our position in the cosmic sea. There is something gently poetic about that, a dead star helping guide us forward. Now, well, the beams themselves are extraordinary. They are not simple shafts of light. They are streams of high-energy radiation, often radio waves, sometimes X-rays, occasionally even gamma rays. They come from charged particles being accelerated along the star's magnetic field lines. Near the magnetic poles, these particles are whipped around, forced into arcs, energized to levels we rarely achieve on Earth. As the pulsar rotates, those beams sweep across space like a cosmic searchlight reaching across billions of kilometers. If you step back in your imagination and watch the neutron star from above one of its poles, you'd see those beams illuminating the dark like spokes from a wheel. If you watch from the side, you'd see flashes, brief and bright, timed with exquisite regularity. Every pulse marks the rotation of the star, and because neutron stars are so stable in their spin, the pulses barely deviate. Some pulsars lose only a fraction of a millisecond over thousands of years. They are clocks built not of metal and engineering, but of collapsed matter and magnetic fields. Pulsars also help us map the galaxy. Their regular signals can be measured from different points in our solar system, allowing us to triangulate positions much like sailors once did with stars. Imagine a future spacecraft, perhaps in the quiet dreams of 2025, something gliding silently between worlds, using pulsars as cosmic signposts, navigating not by Earth's instructions but by the pulsing of dead stars. And sometimes pulsars behave even more dramatically. Some emit not only radio pulses but intense X-ray bursts. Others have pulses that glitch, momentarily speeding up due to sudden movements inside the star. These glitches reveal the presence of the superfluid interior, where quantum vortices shift and rearrange. Think about that. The timing of pulses across thousands of light years carries information about the frictionless flow of neutrons beneath a crust only centimeters thick. A pulsar is telling us, with each beat, what is happening inside its bones. Even more astonishing is that some pulsars turn on and off. They pulse for days, weeks, years, then fall silent, their beams disappearing from our line of sight. Then, in a moment of cosmic whim, they return again, pulsing as though nothing had changed. The star remains the same, but the mechanism of its emission flickers, reminding us that even the most precise clocks can have moods. And perhaps one of the most enchanting ideas is that some pulsars emit multiple beams. Their light cones overlap, cross, and create intricate timing signatures that allow scientists to reconstruct their geometry. It is like reading shadows cast by unseen structures, understanding a star's shape by the patterns of its flickering. If you could watch a pulsar with your eyes, which of course you cannot here on Earth, it would not appear as a flashing point of light. Those beams are often outside the visible spectrum, but if your perception could stretch into radio waves or X-rays, you would see something like a lantern spinning, its beams slicing across your vision with machine-like precision. And I suppose that, in a way, pulsars give us a glimpse of cosmic rhythm. Not the chaotic rhythm of explosions or the slow drift of galaxies, but a steady, heartbeat-like cadence that feels almost intimate. These stars, long dead, still speak in time. There are pulsars in binary systems as well. Imagine a neutron star orbiting another star, both locked in an intricate gravitational dance. Every time the pulsar rotates, its beam sweeps across space, but the orbit adds another layer of motion, shifting the arrival times of the pulses in delicate patterns. By measuring those patterns, astronomers have confirmed predictions of general relativity, including the loss of orbital energy through gravitational waves. A pulsar becomes, in such a system, a testing ground for some of the deepest questions in physics. You know, some pulsars flicker faster as they age, not because they generate new spin, but because they siphon material from a companion star. That material transfers angular momentum, speeding up the neutron star like a cosmic spinner being wound tighter and tighter. These recycled pulsars become the fastest rotating objects we know. Their pulses act as reminders that even stars continue to evolve long after their fiery lives end. Others emit pulses so faint that they disappear for long stretches, barely brushing Earth's detectors. Some have pulse shapes that change slowly, as though the beam itself is drifting like a lighthouse lantern needing occasional adjustment. And, in some extraordinary cases, we have discovered pulsars whose pulses arrive with such stability that they can be used to detect tiny ripples in space-time, caused by distant supermassive black hole mergers. The pulsars become part of a galaxy spanning gravitational observatory. Perhaps it is worth pausing here to imagine the feeling of watching a pulsar signal appear on a radio telescope's screen. The faint tick repeating, unwavering, precise. A star that once roared with nuclear fire now rotates in silence, and yet it sends these whispers across the dark, carrying a rhythm that humanity can detect, measure, interpret. It feels a little like listening to the heartbeat of the cosmos itself. And through all this, the pulsar remains simply what it is. A neutron star spinning rapidly, its magnetic field tilting just enough to let light escape in beams. There is no intention, no purpose in the pulses beyond the physics that produces them. Yet we humans, with our inclination for metaphor, find patterns in the pulses, meaning in their timing. We let their steadiness guide our instruments, inspire our science, and comfort our sense that somewhere out there, the universe keeps order even in its most extreme corners. As the pulsar ages, its rotation slows, the pulses gradually lengthen, the beams weaken. Eventually, perhaps after millions of years, the pulsar quiets. The lighthouse goes dim. The star becomes simply a neutron star once more, without the sweeping illumination. But even then, it continues to shape the space around it with gravity and magnetism. And I suppose that this quieting does not diminish its story. It only reminds us that everything in the universe has phases, rhythms, lifetimes. Pulsars shine brilliantly for a time, guiding scientists and travelers alike before settling back into stillness. Now, as we rest here for a moment in the flickering afterglow of those pulses, another curiosity begins to rise. If these beams of radiation are driven by the star's magnetic field, if the rotation interacts so intimately with magnetism, what then happens when the magnetic field becomes extreme? What if the already intense magnetism of a neutron star grows to monstrous proportions? And so, with the echo of pulses still ticking gently in our thoughts, we drift toward the next mystery. The magnetic realms of neutron stars so powerful they can tear atoms apart, bend matter into strange shapes, and carve their own legends into the fabric of space-time. Well, you see, once those pulses fade softly into the background of our imagination, and we sit there with the quiet rhythm of a spinning neutron star still echoing somewhere inside us, another presence begins to emerge. It's subtler at first, like a hum beneath the hum, a force not made of mass or light but of something stranger, something that threads itself through space with invisible tension. And when you look closely, when you let your senses adjust to this new layer of reality, you begin to feel it, the magnetic field. Not the gentle field that turns a compass needle on Earth, nor even the intense fields that surge through laboratory coils. No, what surrounds a neutron star is a magnetic realm so extreme, so utterly beyond scale, that it stretches language to its limits. The magnetic field of an ordinary neutron star can be 1 trillion times stronger than Earth's. 1 trillion. And that's only the beginning. Here, magnetism becomes not just a force, but a sculptor, reshaping particles, bending light, altering the very behavior of electrons and atoms. It becomes part of the star's personality, woven into its identity just as gravity and rotation are. You know, a field that strong does not simply influence matter, it dominates it. At such intensities, electrons cannot orbit nuclei the way they do on Earth. Their orbits collapse, elongate, distort. The atom becomes something like a pencil, stretched along the magnetic axis, pulled into unfamiliar geometries. Light itself, that swift and elegant traveler, can be affected. Photons scatter differently. Space around the star becomes polarized, meaning light prefers certain directions over others. And, in a quiet, almost eerie way, the magnetic field begins to instruct the universe how to behave. Perhaps picture this. Dust grains floating thousands of kilometers away begin to align along the magnetic field lines, rotating like dancers who suddenly hear the faint beat of a hidden drum. Well, you see, when we follow the trail of magnetic intensity upward from an ordinary neutron star, past the already astonishing fields that twist atoms and bend the paths of light, we eventually arrive at a threshold where the universe seems to pause, take a breath, and then step into something far more extreme. And this is where the magnetar emerges. A magnetar is not just a neutron star with a strong magnetic field. It is a creature of the cosmos that exists so close to the limits of physical law that even speaking about it feels a little like whispering near the edge of a cliff. The magnetic fields here are not merely strong. They are the strongest known anywhere in the universe, stronger than anything the human imagination evolved to picture. Perhaps imagine a field so powerful that it could rip atoms apart from a distance, a field capable of distorting the very shapes of electrons, squeezing their quantum clouds into elongated threads, a field that could, in theory, erase the chemical bonds in your body from thousands of kilometers away. Well, magnetars are born wearing such fields like cloaks woven from pure force. Their magnetic fields can soar 1,000 trillion times stronger than Earth's. And that number is so large it becomes an abstraction. But maybe, if you let yourself drift slowly into the scale of it, it begins to settle into something understandable, something awe-inspiring. A magnetar's field is the universe shouting instead of whispering. You know, the origin of that magnetic fury traces back to the moment of collapse. When the core of a massive star shrinks into a neutron star, its magnetic field is compressed. But in some rare cases, conditions align so perfectly, rotation, convection, internal turbulence, that this compression becomes explosive in effect. The field amplifies itself, feeding on the collapse, winding tighter and tighter, until it hardens into something monstrous. A magnetar is formed in that brief, violent moment, a star whose magnetic power dwarfs every other force save gravity itself. And yet, despite this intensity, the magnetar remains tiny, no bigger than any neutron star turning silently in the dark. Perhaps one of the most startling truths about magnetars is how unstable they are. The magnetic field is so strong that it strains the crust of the star, bending it, twisting it, forcing it into states that cannot last. Imagine the surface of the star like a sheet of metal being torqued by invisible hands. Eventually it cracks, and when a magnetar's crust breaks, the energy released is catastrophic. These starquakes, as astronomers call them, send bursts of radiation sweeping across space. Some of these bursts are so intense that they momentarily alter the ionosphere of Earth even from tens of thousands of light years away. And, think about that. A starquake, on a star you could cross in 20 minutes by car at highway speeds, produces enough power to touch another world across the galaxy. The scale is almost tender in its brutality. Sometimes these quakes trigger even more dramatic events, gamma-ray bursts. Magnetars can unleash outbursts of high-energy light so bright that, for a fraction of a second, they outshine every other star in their galaxy combined. A magnetar does not burn with fire. It erupts with magnetism, and the light we see is the byproduct of that violence. These gamma flashes are so powerful that they can damage satellites orbiting Earth, even though the magnetar itself lies unimaginably far away. And yet, strangely, magnetars are ephemeral. Their magnetic fields decay rapidly, at least compared with the quiet endurance of ordinary neutron stars. The intense field eats itself, feeding the star's outbursts until, after perhaps 10,000 years, a blink in cosmic terms, the magnetar calms. It becomes a quieter neutron star, its storm of magnetism reduced to something less dramatic. And I suppose there is something poetic in that brief, brilliant flare of existence. Magnetars burn not with heat but with magnetic madness, and when that fury is spent, they settle into anonymity. You know, for all their violence, magnetars are rare. Only a tiny fraction of neutron stars ever become them. They require conditions the universe does not often provide. The right rotation rate at birth, the right internal dynamics, the right mass. They are cosmic outliers, the black swans of stellar remnants. Their scarcity gives them a mythic quality, as though the universe occasionally produces one, just to remind itself what extremes are possible. Even the space around a magnetar is haunted by its field. Dust grains align for millions of kilometers. Charged particles are whipped into spirals so tight they glow with X-rays. The vacuum itself becomes polarized, behaving not quite like empty space anymore, but like a medium shaped by the field. Light slows, shifts, refracts. A magnetar turns the world around it into a theater where the laws of physics perform in ways that, until recently, we only imagined. And, when a magnetar interacts with a companion star, though this is rare, the effects can be spectacular. Its magnetic field can strip material, distort stellar winds, and ignite bursts that ripple outward. Even planets, were they unlucky enough to exist near such a star, would be torn apart by magnetic shear. Magnetars do not have habitable zones. They have hazard zones radiating outward for astronomical distances. Sometimes their surfaces crack not once, but repeatedly. Each quake sends vibrations through the star's interior, and those vibrations tell us about the mysteries beneath the crust. The core of a magnetar may be filled with superfluid neutrons or even stranger forms of matter. The magnetic field couples with this unseen interior, creating oscillations we can detect across light years. In that sense, magnetars allow us to listen to the inside of a neutron star, something no laboratory on Earth could ever accomplish. Perhaps what fascinates me most is how magnetars embody contradiction. They are both ephemeral and eternal, violent and beautiful, rare and yet profoundly influential. For all their brief active lifetimes, they shape galaxies through their bursts, sprinkle elements across space, and leave behind remnants that continue affecting cosmic evolution long after their magnetic fury has cooled. And as we sit here in the quiet corridors of thought in 2025, imagining that crackling surface, those invisible coils of magnetic tension, the slow decay of a colossal field unraveling through space, we might begin to sense a deeper question forming. If magnetars represent the extreme of magnetic force, if they bend matter and light and even space to their will, then what happens when two neutron stars, magnetar or not, collide? What happens when gravity and density and magnetism all combine in a moment of catastrophic union? And so, gently, almost with a sense of awe, we drift toward that next cosmic story, the moment when two massive remnants meet, and the universe trembles with waves that ripple through space-time itself. Well, you see, after we've stood in the magnetic storm of a magnetar and felt that enormous tension humming through space-time, there's a kind of quiet that settles over the imagination, a quiet that is not the absence of sound, but the gathering of forces preparing for something immense. And, when two neutron stars drift toward one another, slowly over millions or billions of years, that quiet becomes a kind of cosmic breath held in anticipation. Because when these two remnants finally meet, the universe does not merely witness a collision, it listens to a shudder that travels across existence itself. Perhaps imagine them first from far away. Two tiny stars, each only 20 kilometers across, each dense enough to warp space into deep gravitational bowls, orbiting one another like dancers bound by an ancient rhythm. Their orbit shrinks with time, not because they lose momentum in the usual sense, but because they radiate something subtle and profound, gravitational waves. These waves ripple outward, carrying away energy, distorting space-time with every cycle, and you know the dance quickens, spiraling closer, faster, tighter. As they draw nearer, the frequencies of these waves rise, like a cosmic violin string being tightened. If you could listen to their in-spiral translated into sound, and in a way, detectors like LIGO have done exactly that, you would hear a rising chirp, a soft sweep upward, gentle at first, then sharper, faster, almost urgent. It is the universe whispering the approach of something extraordinary. And when the stars finally collide, the violence defies language. But it is not the explosion that first announces the event. It is the waves in space-time. These waves race outward at the speed of light, expanding like ripples on a dark cosmic sea. They travel for millions of years until they finally reach detectors on Earth, faint tremors in instruments so delicate they can sense changes smaller than the width of a proton. Yet the story they carry is enormous. They tell us that two neutron stars have merged, that matter has been crushed and torn apart, that a new object has been formed, perhaps an even more massive neutron star, or perhaps a black hole. You know, what follows the gravitational waves is equally astonishing. Light. Glorious, energetic light. The collision produces a kilonova, a brief but spectacular explosion far less energetic than a supernova, but far richer in meaning. For in that explosion, the universe forges heavy elements, not in the heart of an ordinary star, not through the slow burning of nuclear fusion, but in the violent alchemy of two collapsed stars ripping each other open. Gold, platinum, uranium. These are born in the frenzy of neutron-rich debris hurled into space. Perhaps pause with that for a moment. The gold in a wedding ring, the platinum in electronics, the heavy elements in Earth's crust, many of them were created in moments like this, in cosmic collisions that happened long before the sun was born, long before Earth cooled, long before humans shaped tools or crafted stories. It is humbling, almost comforting, to realize that we carry in our bodies matter forged in the crash of dead stars. The kilonova glows with colors we cannot see directly, rich in infrared light. It expands like a luminous cloud, enriched with the ashes of nuclear creation. These ashes scatter through galaxies, drifting for eons until they become part of new solar systems, new worlds, new living beings. A collision so violent it warps space-time also becomes, strangely, beautifully, a source of the materials that build civilizations. And as the neutron stars merge, the physics inside that brief moment becomes almost incomprehensible. The densities spike, temperatures rise to billions of degrees, and matter is compressed so violently that even the neutron star state becomes unstable. Some of the matter is shredded into streams of neutrons. Some is swallowed by the new core. Some is ejected outward in arcs, moving at a significant fraction of the speed of light. And, in that chaos, something elegant happens. The R process. A rapid neutron capture that creates heavy elements in seconds. On Earth, forming these elements takes intense laboratory effort. In a neutron star merger, the process unfolds naturally, spontaneously, as if the universe has been waiting for these moments to express one of its most intricate mechanisms. Astronomers have observed these kilonovae both through gravitational waves and through electromagnetic light. It is the first time in human history that we've watched the universe in two languages at once: the silent shiver of space-time and the radiant bloom of exploding matter. The merger detected in 2017 was a revelation. Suddenly, we could see how the universe weaves heavy elements. Suddenly, we could confirm theories once only written in equations. You know, these collisions also reshape nearby space. The gravitational energy released can send shockwaves through surrounding gas clouds. The resulting winds can blow cavities into interstellar material, seeding the cosmos with enriched debris. Some of this debris might someday settle into new disks of material around young stars. And perhaps in those disks, planets will form. And perhaps on those planets, someone else will one day wonder where their atoms came from. Even after the merger, the story is not quite over. If the outcome is a rapidly spinning massive neutron star, it may emit intense radiation for a short time. If it collapses into a black hole, matter swirling around the event horizon can produce jets, narrow beams of relativistic particles that shoot across space. These jets may appear as short gamma-ray bursts, some of the most energetic flashes in the universe. Imagine that. A millisecond of brilliance carrying the energy of an entire galaxy. And I suppose there is something beautifully cyclical about this. The collision that ends the lives of two neutron stars becomes the beginning of countless atoms, countless worlds, countless stories. The universe does not waste its tragedies. It reworks them. Perhaps one of the most mysterious aspects is how the gravitational waves encode information. They reveal the masses of the stars, their distance, even clues about the stiffness of neutron star matter, the equation of state that we still do not fully understand. The waves carry secrets of the star's interior, of pressures and densities we cannot produce on Earth. Listening to these waves lets us touch physics far beyond anything we can recreate. As we move further into these ideas, we begin to see neutron star mergers not just as catastrophic events, but as cosmic laboratories. Each collision writes data into space-time itself, and we, with delicate detectors on Earth, read that data like archaeologists of the universe. The waves allow us to test relativity, nuclear physics, astrophysics, and cosmology all at once. And in another curious way, these collisions explain part of who we are. The iron in our blood may come from a supernova, but the gold we cherish, the platinum we refine, those likely came from the merger of two neutron stars. You and I carry in our atoms the remnants of stars that once spiraled toward each other in the deep silence of space. It is a strange kind of ancestry, a cosmic lineage written in the periodic table. Now, as we sit here in the softness of night, letting that truth settle, the idea that the universe shakes when neutron stars collide, that space itself ripples, that matter is reborn in fire and gravity. Another thought begins to rise. If these collisions reveal so much about neutron star interiors, about matter flung outward, about gravitational waves radiating into the cosmos, what then of the star itself? What lies beneath its surface? What hidden layers does it carry inside, waiting for us to imagine? And so, gently, as though turning a page in a book written in starlight, we drift toward the next chapter of this journey. The strange and layered structure of a neutron star's surface and the exotic mysteries buried deep within. Well, you see, after witnessing the grand collision of two neutron stars and feeling the universe tremble with gravitational waves, we are left with a strange longing to understand what these stars truly are beneath their violent interactions. We've watched them shatter each other, forge gold, ripple space-time. But what about their quiet inner lives? What about the hidden, layered worlds beneath their surfaces? And as we drift closer in imagination, approaching one of these dense remnants, we begin to sense that its outward simplicity hides a structure so bizarre, so profoundly alien, that even the wildest visions of science fiction fall short. From afar, a neutron star appears almost modest, a small, dim sphere no wider than a city. But the moment we allow ourselves to imagine standing near it, or hovering just above that haunting surface, everything shifts. The crust beneath us is not rocky, not molten, not anything we might call familiar. It is a crystalline lattice of neutron-rich matter, a structure harder and stronger than anything we know on Earth. Some scientists imagine it as a kind of nuclear crystal, rigid and nearly perfect, with pressure so immense that even the tiniest flaws are pressed into obedience. You know, this crust is only centimeters thick before the world begins to change beneath it, just centimeters. The transition from the hardest material in the universe to an ocean of superfluid beneath is abrupt, almost theatrical. If the crust were glass, the layer beneath would be dreamlike water, except this water has no viscosity, no friction, no resistance. It flows eternally, perfectly, endlessly. A neutron, superfluid. A quantum liquid spreading through the star's interior like an echo of the laws that govern atoms, but scaled up to celestial size. And that's the thing. Nowhere else in the universe do we see matter behaving like this. Not in planets, not in main sequence stars, not even in black holes, which have no interior matter at all. Only neutron stars carry this strange layering, crust, superfluid mantle, and perhaps deeper still, a core whose true nature remains a whispered mystery. Some theories suggest that the core contains quark matter, where neutrons dissolve into their constituent quarks, up down, perhaps even strange quarks, forming a soup so dense and so exotic that it defies every analogy. Others suggest phases of hyperons, particles that flicker into existence only under pressures no laboratory on Earth can achieve. And, the truth may be that multiple phases coexist, stacked and intertwined in ways we have not yet imagined. The neutron star, from surface to center, becomes a museum of extreme states of matter. If you could somehow peel back the layers, though of course you would be crushed beyond recognition long before, the star would reveal a gradient of density increasing as you descend. The crust, rigid and crystalline. The inner crust, threaded with nuclear pasta structures, sheets and tubes of matter arranged in bizarre shapes with names like lasagna and spaghetti, born not of whimsy but of the strange interplay between nuclear attraction and repulsion at extreme densities. These shapes minimize energy, forming naturally as matter tries to negotiate impossible forces. They represent, perhaps, one of the universe's most unlikely works of art. Below that lies the superfluid, gliding silently beneath the crust. And this superfluid does not simply sit there. It swirls in quantized vortices, tiny rotating structures that align neatly with the star's spin. These vortices anchor themselves to the crust, and sometimes they pin, refusing to move. This mismatch between the superfluid's motion and the crust's rotation leads to those glitches we spoke of earlier. Sudden jumps in rotational speed that echo through space. A jolt, a slip, a cosmic tremor in the heartbeat of the star. And deeper still, as we approach the monstrous densities of the core, the familiar breaks down entirely. The neutrons are packed so tightly that their quantum identities may blur. A single cubic centimeter of this core would outweigh mountains. If lifted somehow, impossible though that may be, it would annihilate any ordinary matter it touched merely by existing. And, in that central region, temperatures soar to millions of degrees. Even in its cooling phase, the neutron star radiates blistering heat, glowing with intense X-rays. The surface temperature alone can reach 1,000,000 degrees, though from afar the star appears faint and cold. What's fascinating, and quietly unsettling, is how smooth the surface is. A neutron star might have mountains, yes, but these mountains rise only centimeters high. Even the tallest peaks cannot withstand the star's gravity. They are pressed flat almost immediately. The surface becomes an impossibly smooth sheet of nuclear crystal, reflecting none of the rugged complexity of terrestrial landscapes. And that smoothness, that rigidity, combined with the intense pressure, makes the crust capable of supporting stresses that would shatter worlds. When it does break, the result is a starquake, a violent rearrangement of the crust that can release enough energy to alter the star's rotation or unleash bursts of radiation into space. Imagine the sound of a mountain range snapping in an instant, except amplified across an entire star. And yet, for all this extremity, the neutron star's surface is quiet, not in the sense of temperature, which is blistering, but in the sense of motion. No winds, no waves, no storms, no atmosphere to stir. The surface is bare, stripped of air, stripped of oceans, stripped of everything but pure nuclear matter. Standing there, if one could stand, would feel like standing at the edge of existence itself, where matter has been stripped down to its fundamental forms. One of the great mysteries that lingers is the exact composition of the core. It is the most inaccessible place in the universe, not because it is far, but because it is locked behind pressures that prevent any spacecraft, any probe, any instrument from reaching it. Our only tools are observation and theory, and so, neutron stars become puzzles we solve by listening to their pulses, their quakes, their collisions. Their surfaces hide the secrets of the interior, but the clues escape in signals we can measure. The very existence of such a layered structure, crust, inner crust, superfluid mantle, exotic core, challenges our understanding of matter. It suggests that the universe contains phases of matter we have not yet created, not yet modeled fully, not yet seen, except through the behavior of these stars. That is why neutron stars are called laboratories of extreme physics. They carry inside them answers to questions we have not properly learned to ask. And, When you consider the pressures involved, pressures that bend atomic nuclei, that force matter to organize itself in patterns unlike anything on Earth, it becomes clear why neutron stars break the boundaries of classical physics. In their interiors, quantum mechanics reigns not at the scale of particles, but at the scale of kilometers. Entire regions of the star behave like superatoms, unified and coherent. Even the light the star emits carries hints of its inner life. X-ray emissions vary depending on the structure of the crust, the presence of hotspots, the decay of magnetic fields. Observing these emissions lets us map temperature gradients on the surface, revealing, faintly, the stresses within. And perhaps what moves me most is that, despite all this extremity, neutron stars are stable. They persist. Their crusts hold. Their superfluids flow. Their cores endure pressures that would annihilate anything else. And they do so for millions of years, slowly cooling, slowly dimming, but never collapsing unless forced by added mass. Now, as we let our minds rest gently on this layered world, this impossibly dense, impossibly hot, impossibly structured relic of a once brilliant star, another question begins to stir. If the interior of a neutron star is so hostile, so extreme, so utterly unlike anything life could tolerate, then what does that say about the possibility of life near such a star? What does it say about life's relationship to the cosmos? And so, as though stepping from the harsh interior of a star into the quiet wonder of reflection, we drift toward the next chapter, the strange and sometimes surprising relationship between neutron stars and the very elements that make living beings possible. Well, you see, after wandering through the interior of a neutron star, after touching that crystalline surface and imagining the superfluid depths beneath, something soft and very human begins to rise in us. A question that feels almost innocent compared with the violent physics we have just crossed. It is the question we always seem to ask whenever we look outward into the night. Could life ever exist near such a place? Could anything living, anything breathing, anything aware, find a home in the shadow of a neutron star? And, the answer comes quickly, sharply, almost before the question fully forms. No. Not life as we understand it. Not life of any familiar chemistry. A neutron star is one of the most hostile environments in the cosmos. Its radiation alone would strip molecules apart before they even had the chance to organize. Intense X-rays, gamma rays, bursts of magnetic fury, all of it conspires to erase complexity. The gravity would crush every structure. The temperature would vaporize matter. There is no atmosphere, no gentle warmth, no stable surface upon which biology could take root. There is only pressure and fire, and the strange, condensed heart of matter. But that's the thing, and perhaps the beautiful twist in the story. Even though neutron stars cannot host life, they help create the ingredients for it. They are terrible places to live, yes, but they are generous ancestors. It is as though the universe sometimes appoints the most violent objects as the caretakers of creation. When a neutron star forms, and especially when two neutron stars collide, they forge elements that life on Earth depends on. Maybe you've heard the phrase before that we are made of stardust, and that is true, but perhaps not in the way we often imagine. The iron in your blood, for example, was made in the core of a dying star. The calcium in your bones came from nuclear reactions in ancient stellar furnaces. But some of the heaviest, most precious elements, gold, platinum, uranium, those came from neutron stars themselves. Imagine that for a moment. Matter that once belonged to a collapsed star, matter squeezed into densities that defy the imagination, now rests quietly in your jewelry, your tools, even in small traces within your own body. The gold in a wedding ring may have been born in the instant two neutron stars tore each other open and scattered their interior layers across space. That gold then drifted through the galaxy for billions of years, wandered through gas clouds, mixed into the dust that eventually formed the sun, the earth, and everything that lives here. And I suppose there is something humbling in that, something almost tender. We are, in a very real sense, the descendants of dead stars. But even beyond the heavy elements, neutron stars contribute to the shaping of planets, stars, and galaxies. Their explosions and collisions enrich interstellar gas, seeding it with materials needed for worlds to form. Without them, the universe might remain a place of simple elements, lacking the complexity that life requires. The carbon in our cells, the phosphorus in our DNA, the metals that power our technology, all of it exists because stars die, because neutron stars arise, because their lives and deaths enrich the cosmos. Sometimes I think of neutron stars as cosmic recyclers. They take the simple hydrogen that once filled the early universe, processed through earlier generations of stars, and transform it into the deep, layered richness that becomes planets, flowers, oceans, and people. Life cannot live near them, but life cannot exist without them. It is a paradox that the universe seems almost proud of, and even the violence of neutron stars holds meaning for us. Their magnetic storms, their bursts, their gravitational waves, these phenomena shape the environments around them. They influence star formation. They sculpt nebulae. They carve patterns in the interstellar medium. From thousands of light years away, their presence subtly nudges the evolution of galaxies, ensuring that no region of space remains static for too long. Yet, in all of this, the most profound connection between neutron stars and life is philosophical, rather than physical. When we say that we are stardust, we're acknowledging a lineage that transcends biology. We're saying that the atoms in our bodies come from processes older than Earth, older than the Sun, older even than our spiral arm of the galaxy. We are the continuation of matter shaped in cosmic extremes. The universe looks at itself through the eyes of beings made from neutron star debris. That thought, I suppose, is both overwhelming and comforting. It places us in a story that is vast, ancient, and ongoing. And perhaps this is where we find the truest meaning of neutron stars in the context of life. Not that they host it, not that they nurture it, but that they remind us of the transformative power of the universe. They show us that life emerges not in spite of cosmic violence, but partly because of it. They are monuments to the cycles of creation and destruction that allow complexity to arise. Sometimes I like to imagine a kind of quiet poetry in this, a neutron star spinning alone in the darkness, unaware of the worlds that will one day be built from its remnants, unaware that creatures of water and bone and thought will look up at the night sky and wonder where they came from, unaware that its death or its collision will echo in the blood and bones of beings that have not yet evolved. The star does not intend it, of course, but intention is not required for beauty to occur. In the calm hours of a night in distant ages from now, maybe in 2025 or beyond, a person might hold a piece of gold in their hand and not know that it was born in the fire of a merging neutron star. But the truth remains. Whether it is known or not, the universe lives in everything that lives. And so, after drifting through these reflections, after feeling the strange closeness between our own bodies and the most violent objects in the cosmos, another question gently rises. If neutron stars reveal so much about life, not through hospitality but through ancestry, what might they reveal about the future of our understanding? How might they guide us, teach us, challenge the boundaries of physics and technology? And with that soft wondering, we step forward toward the next chapter, the future of science shaped by neutron stars, and the doors these cosmic laboratories may yet open for us. Well, you see, once we've traveled through the strange relationship between neutron stars and the elements that make life possible, something begins to open in the mind. A sense that these stars are not only relics of the past, but also signposts pointing toward the future of human understanding. And, perhaps this is where the story evolves from wonder into purpose. Because neutron stars and their quiet, intense existence offer scientists some of the most profound opportunities for discovery anywhere in the universe. They are not just celestial corpses. They are, in a very real sense, laboratories where the most extreme laws of nature are written plainly across the sky. In the fields of quantum physics, neutron stars stand as examinations we cannot administer on Earth. Their densities, their pressures, their temperatures, their magnetic fields, all of them stretch the limits of theoretical models. Studying neutron stars helps physicists test quantum mechanics under conditions no particle accelerator can replicate. For example, understanding how neutrons behave at such extreme densities offers clues about the fundamental forces binding matter. Every pulse, every glitch, every gravitational wave emitted by a neutron star becomes a piece of data that refines our models, reshapes our equations, and forces us to rethink the structure of reality. And that's the thing. Neutron stars do not simply encourage deeper physics, they demand it. Even Einstein's theory of general relativity, which has stood firm for over a century, finds its most intense examinations in these stars. The curvature of space-time around a neutron star is severe enough to test relativistic predictions with exquisite precision. How light bends near them, how time slows at their surfaces, how binary neutron stars spiral inward, all of it becomes a cosmic classroom for relativity. Observations of neutron stars have confirmed, again and again, the astonishing accuracy of Einstein's ideas. But they also hint at places where our theories might evolve, especially at the border where relativity meets quantum mechanics. And, that border remains one of the deepest mysteries in science. In the future, neutron stars may help us finally unify these two great pillars of physics, quantum theory and gravity. That sounds ambitious, even poetic. But the truth is that the universe already contains the answers. They're written in the interiors of neutron stars, waiting for us to learn how to read them. And beyond pure physics, neutron stars hold profound relevance for space exploration. Their incredible regularity, especially the heartbeat-like pulses of pulsars, can serve as natural galactic navigation beacons. Imagine spacecraft in the distant future sailing between star systems, guided not by Earth-based signals, but by pulsars scattered across the galaxy. Each pulse, so precise it rivals an atomic clock, becomes a point of reference, a cosmic lighthouse, a guidepost in the vast map of the Milky Way. Perhaps, in a quiet moment aboard a starship in some distant century, a navigator will whisper a thank you to a spinning neutron star that helped them find their way home. And, the study of neutron stars also deepens our understanding of where the elements come from. By observing how neutron stars collide and detecting the resulting gravitational waves and kilonova light, scientists can refine models of nucleosynthesis, the creation of new atomic nuclei. This helps us determine how galaxies evolve, how planets acquire their compositions, how life gains its building blocks. Understanding neutron stars means understanding the ancestry of matter itself, and that gives us a clearer sense of our own cosmic origins, as well as the potential diversity of worlds elsewhere in the universe. Neutron stars also serve as markers for predicting the life cycles of other stars. By studying their properties, their spin rates, their cooling curves, their magnetic fields, astronomers can better predict when stars will explode, how they will collapse, what remnants they will leave behind. Every neutron star becomes a clue, a cipher in the long story of stellar evolution. And as we observe more of them, as our telescopes and detectors grow sharper, we will refine our models of how the universe recycles its matter through generations of stars. You know, there is also something wonderfully forward-looking about the way neutron stars allow us to simulate exotic physics. When theorists attempt to model the interior of a neutron star, they must push their equations beyond comfort, into regions where matter behaves unexpectedly, where superfluids swirl beneath crystalline crusts, where magnetic fields bend quantum states. These simulations teach us about matter at its limits. They may even guide new technologies someday, though that remains a distant dream. Still, the act of understanding extreme physics often leads to unexpected pathways, just as studying electromagnetism once led to radio, studying plasmas led to fusion research, and studying relativity led to GPS. And, perhaps there is something gently humorous in imagining the technologies of the future inspired by stars so dense they cannot be touched, so violent they cannot be approached. Yet that is often how science works. The universe invents physical scenarios we cannot recreate, and by observing them, we learn new ways to shape our own world. Another quiet promise of neutron star research lies in understanding the shape of space-time itself. By mapping how gravitational waves move through the cosmos, we begin to create not just a static picture of the universe, but a dynamic one, a living map of shifting space-time. Neutron stars give us data about this curvature, allowing us to test predictions about how the universe stretches, bends, and evolves. The future of cosmology will depend heavily on our ability to interpret these signals, to read the ripples like geologists read seismic waves on Earth. Even the act of locating neutron stars helps refine our cosmic navigation. Their positions, their timing patterns, their relationships with surrounding space contribute to a new era of galactic mapping. Perhaps in the centuries ahead, future explorers will rely on neutron stars as reference points much as ancient sailors relied on Polaris. But beyond all the scientific promise, neutron stars offer something more fragile and more profound. They offer perspective. Each neutron star reminds us that the universe is far stranger and more inventive than our intuition allows. It shows us, gently but firmly, that our understanding is always provisional, always growing, always open to revision. In the presence of neutron stars, our philosophical humility deepens. We recognize that the cosmos is not obligated to follow rules we find comfortable. Instead, it invites us to expand our imagination, to stretch our minds to match its scale. And as we think about the future of science shaped by these dense remnants, perhaps we also think about the doors still unopened, the mysteries of quark matter, the limits of superfluid behavior, the true nature of strong nuclear forces at stellar densities. These are frontiers waiting quietly for us, waiting in the pulse of a distant star, waiting in the faint tremor of a gravitational wave, waiting in the slow cooling of a crust that once blazed white-hot. In the gentle quiet of a night somewhere in the era of 2025, a student listening to the hum of data from a neutron star might find themselves wondering whether the universe is nudging us toward some deeper coherence, a unification of physical laws that we have not yet glimpsed. And perhaps they will be right. And now, as we drift from the scientific future toward something broader and more contemplative, another thought begins to bloom. If neutron stars challenge our theories, expand our sciences, and shape our explorations, then what do they say about us? What does our fascination with them reveal about the human need to seek, to question, to imagine? With that gentle wondering at the edge of our thoughts, we move toward the final reflection of this journey, where the story of neutron stars becomes, in a subtle way, the story of ourselves. Well, you see, after wandering through the scientific horizon that neutron stars open for us, through the quantum frontiers, the gravitational laboratories, the cosmic navigation systems of tomorrow, there is a moment when the science gently dissolves into something broader, something a little more human. And, perhaps that is where a new chapter naturally begins, one that isn't only about what neutron stars are, but about what they mean to us. Because every time we gaze outward into the dark and listen to the pulses of these collapsed suns, we're not just gathering data. We are, in some quiet and earnest way, learning about ourselves. And I suppose that's the curious thing. The deeper we study neutron stars, the more they seem to hold up a mirror to the nature of human curiosity. These stars are unreachable, untouchable, dead, and yet expressive, silent, and yet full of signals. They remind us that the universe is vast beyond measure, indifferent to our existence, and yet astonishingly generous in the mysteries it reveals. Why, then, do we keep listening? Why do we care about objects that will never know we exist? Perhaps because our fascination with neutron stars says something essential about us, something delicate and persistent. You know, when early astronomers first detected regular pulses from the sky, they wondered if they were signals from another civilization. Little green men, some joked. Imagine that. Humanity searching for meaning in the ticking of a dead star. In a way, even though we now know these pulses come from rotating neutron stars, that yearning hasn't gone away. Each pulse still feels like a message. Not a message to us, but a message about the universe, about the laws that shaped it, about the places where those laws stretch to their breaking point. And, when we sit here imagining neutron stars in the quiet hours of a night in 2025, we might realize that our fascination isn't just intellectual, it's emotional. There is awe in it, a kind of reverence, a sense that the universe is not just a collection of facts, but a landscape of experiences waiting to be felt. Neutron stars are part of that landscape, perhaps the most extreme cliffs and chasms in the cosmic terrain. We admire them the way one might admire a storm, fearful but grateful for the reminder that nature is so much larger than us. I suppose neutron stars also teach us about limits, the limits of matter, the limits of physics, and our own limits as thinkers and explorers. They show us where current theories collapse, where our intuitions fail, where we must invent new ways of asking questions. In that sense, neutron stars challenge us, and being challenged is deeply human. We grow through it. But there is something else too, something more subtle. Neutron stars remind us that transformation is woven into the fabric of the cosmos. A massive star burns bright, collapses violently, and then becomes something new, not gone, not erased, but changed. And if the universe transforms itself so radically, perhaps that is permission for us to transform as well, to collapse old assumptions, to compress our scattered understandings into something denser, deeper, truer. And, consider the way neutron stars relate to time. Their pulses can be steady for millions of years, a cosmic heartbeat echoing through the galaxy. And yet they also evolve, slow down, grow quiet. They endure, but not eternally. They are stable, but not immutable. They hold a balance that feels strangely familiar to our own lives. Long arcs of stability punctuated by sudden shifts, moments of crisis, and quiet declines. Perhaps that is why their pulses feel so comforting. They are steady but not static, something like us. And when two neutron stars finally collide, the universe listens. Space itself bends, elements are forged, new worlds become possible. From destruction comes creation. The cosmos is always recycling itself, always finding new ways to arrange matter and energy. And maybe, in a symbolic way, neutron stars remind us that endings are rarely absolute, that in loss there can be beginnings, that in collapse there can be renewal. You know, sometimes I imagine a future child, someone living in a century far beyond our own, watching a neutron star pulse on a holographic screen, listening to its rhythm translated into soft sound. And perhaps that child will experience a moment of the same quiet awe we feel now. Not because they understand the equations, but because they sense the immensity behind them. And that is something neutron stars do remarkably well. They connect generations across time. Every discovery we make now about them becomes part of a chain of understanding that stretches into the future. And, neutron stars also reveal something profound about perspective. From the vantage point of such extreme physics, our everyday concerns feel both tiny and precious. Tiny, because compared to the pressures in a neutron star's core, our stresses are nothing. And precious, because we are made of material forged in cosmic furnaces. The calcium in our bones once lived inside exploding stars. The iron in our blood once glowed in a supernova. The gold we find beautiful once erupted from the collision of neutron stars. How strange and wonderful that biology, thought, emotion, all of it emerges from the ashes of collapsed suns. And I suppose that brings us to another layer of meaning. In studying neutron stars, we are not just learning about astrophysics. We are learning about the story of matter itself, about how the universe writes its autobiography in atoms, and we, being made of those atoms, are part of that story whether we know it or not. Neutron stars remind us that we exist because the universe experimented with extremes. Without their violence, their pressure, their eruptions, there would be no gold in our rings, no iron in our blood, no planets beneath our feet. It is humbling, but also empowering. Because if we come from neutron stars, then we come from resilience, transformation, and unimaginable intensity. Our existence is the quiet aftershock of cosmic extremes. And there is another dimension, one that feels almost philosophical. Neutron stars show us that the universe does not need to be understandable to be beautiful. In fact, the beauty often lies in the mystery, in the questions we cannot yet answer, in the limits we have not yet crossed. Our pursuit of neutron stars is driven not only by science, but by a human longing to feel connected to something vast, something eternal, something beyond ourselves. And, the more we learn, the more the mystery deepens. We uncover a layer, only to find another beneath it. We explain a burst of radiation, only to encounter a stranger burst that defies explanation. We map gravitational waves, only to discover new questions encoded in their frequencies. This endless unfolding is part of the magic. Neutron stars in their silence behave like cosmic teachers. They do not speak, yet they reveal. They do not change for us, yet they transform our understanding. They sit at the crossroads of physics and philosophy. They remind us that the greatest truths often lie beyond what our senses can perceive. And perhaps that is why, even after a long journey through their science and their symbolism, we still feel drawn toward them. They are anchors of mystery in a universe that is otherwise too large, too chaotic, too indifferent to grasp completely. Neutron stars give us structure. Not physical structure, but conceptual structure. They help us make sense of extremes. They encourage us to keep asking questions. So here we are, standing metaphorically at the edge of one of the densest objects in the cosmos, looking inward and outward at the same time. And as we do, another thought begins to glow softly on the horizon of the mind. If neutron stars teach us about physics, about matter, about ourselves, then what remains to be said? What final reflection does this journey invite us to hold? And with that gentle wondering settling around us like starlight, we drift toward the final chapter, where the story of neutron stars becomes a story not only of science or symbolism, but of the universe's enduring ability to astonish and our enduring hunger to understand it. Well, you see, after journeying through these dense, spinning relics of collapsed suns, after watching them pulse, collide, bend space-time, forge elements, and whisper the oldest laws of nature, we arrive at a kind of quiet clearing in the mind, a place where the science softens, where the noise of equations fades, and something more intimate begins to glow. Perhaps this is the space reserved for endings, or at least for the reflection that comes before one. And, standing here, with everything we have learned shimmering around us like faint starlight, we begin to understand why neutron stars capture the human imagination so deeply. They are, in a way, monuments to the extremes of the universe, not just objects out there in the dark, but testimonies, silent, unwavering testimonies to nature's breathtaking power. They show us what happens when a star's core collapses beyond the reach of ordinary physics, when matter is pushed until it becomes something fundamentally new. A neutron star is a reminder that the universe is not merely vast, it is resourceful, daring, unafraid to explore states of existence that we can barely describe. And I suppose that's why the more we study them, the more they unsettle and inspire us. They reveal where classical physics breaks. They reveal where intuition dissolves. They remind us that the cosmos is not designed for our comfort or understanding. And yet, somehow, we can still understand it, at least in glimpses. Every neutron star is a kind of cosmic puzzle box, and the moment we open one layer, another, more mysterious layer appears beneath. You know, sometimes I think the beauty of neutron stars lies not only in what they are, but in what they force us to confront. They push us toward the edges of our intellectual courage. They nudge us to admit how little we know. And, there is a sort of humility in that. A humility that feels necessary in an age when we often imagine ourselves masters of the universe. Neutron stars whisper that mastery is an illusion, that curiosity, not control, is the real path to understanding. And perhaps the deepest lesson they offer is this: the universe is always more than it appears. A neutron star, no wider than a city, contains the mass of a sun. Something that looks like a quiet point of light can, in reality, be a storm of magnetic fury or the steady ticking of a cosmic clock. Something dead can still speak. Something collapsed can still shine. Something destroyed can still create. Transformation at every scale. And that brings us gently to the next truth neutron stars reveal: that the universe, despite its violence, sings with order. Pulsars beat with rhythms so precise they rival atomic clocks. Starquakes release energy with perfect mathematical signatures. Gravitational waves ripple outward from mergers with patterns that equations predicted long before we could detect them. It is as though neutron stars prove that behind chaos lies structure, behind catastrophe lies coherence. And, the idea that the universe is at once wild and ordered, unpredictable yet lawful, destructive yet creative, that idea resonates with something deep in us. It mirrors the contradictions of our own lives. We experience collapse and creation. We endure pressure and become something new. We lose energy and discover new forms of motion. We pulse. We slow. We shine in strange, quiet ways. In the gentle stillness of a night somewhere in 2025, when someone hears the soft hum of radio signals from a distant pulsar, or sees an illustration of a magnetar cracking open its crust, they might not be aware of all the physics involved, but they will feel something. Wonder, maybe, awe. A recognition that this universe we inhabit is astonishingly intricate and unreasonably beautiful. Neutron stars also teach us that the universe is not simple, and that its complexity is not a flaw, but a feature. If everything behaved like stones and steam and sunlight, if matter never dared to push itself beyond the familiar, the cosmos would be quiet, monotonous, uninteresting. Instead, nature invents neutron stars. It invents quark soup and nuclear pasta and magnetic fields that can tear atoms apart. It invents collisions that forge the gold we cherish. It invents gravitational waves that let us listen to the universe stretching. And I suppose the most moving part of all this is how these distant, unapproachable stars help us understand our own limits. They remind us that our minds are small, wonderfully small, but capable of grasping truths that the universe did not design us to comprehend. We evolved to survive on a blue world, with gentle gravity and warm sunlight, not to calculate pressures 1,000,000,000 times greater than anything we can experience, not to imagine the superfluid heart of a star, not to read messages encoded in space-time itself. And yet, here we are, doing precisely that. There is something heroic about that, something quietly noble. Humanity, fragile as dust, looking into the heart of collapsed suns and daring to understand. It is a kind of cosmic defiance, a soft rebellion against ignorance, a way of saying, with all our limits, that we still belong here, in this vast, impossible universe. And, maybe neutron stars also teach us patience. They cool slowly, dim slowly, age slowly. Their stories unfold over millions of years, and in watching them, we are reminded that our own questions need not be answered in a hurry. Curiosity can stretch across generations. Scientists build on the work of their predecessors, just as stars pass matter into new stars, and those into new worlds. Knowledge is itself a kind of cosmic cycle, but there is another feeling too, a quieter one. Neutron stars remind us that even the most compressed, most extreme places in the universe contain mystery. Mystery is not a void, it is a landscape. It is not absence, it is invitation. Neutron stars invite us to keep asking, keep listening, keep imagining. As long as we do that, we remain participants in the universe's unfolding story. And perhaps that is why, at the end of this long journey, we don't feel closure so much as continuation. Every neutron star we discover adds a new thread to the tapestry. Every gravitational wave detection opens a new doorway. Every pulse we record becomes another heartbeat in the cosmic rhythm we are only beginning to understand. So here, at this soft threshold between knowledge and wonder, we take a quiet breath. We look back at the path we've taken, through collapse, density, magnetism, rotation, fusion, and the interior life of stars, and realize that the journey has been less about neutron stars themselves and more about the way they reshape our sense of the universe. And now, with that realization settling gently upon us, another thought rises on the horizon. If neutron stars are this strange, this beautiful, this full of lessons, then what other cosmic wonders might be waiting out there? What new extremes lie beyond even these dense remnants? What new chapters are waiting to be written as our telescopes sharpen, our detectors grow sensitive, and our imaginations expand? And so, without closing anything, without ending the story, we simply turn the page, drifting onward toward the next frontier, where the universe once again invites us to listen, to marvel, and to wonder at what else might be out there beyond the reach of our current understanding.